Today, I'm going to make a presentation on verification and validation using systems engineering methods. Harvard School of Public Health published that on an annual basis, you are 10 times more likely to be struck by lightning than be killed in a plane crash. Why? Because of rigorous verification and validation of sensors and systems in aerospace. The sensors and software verification and validation in the aviation industry is governed by a standard, an international standard, DO 178C, which also has a European code as well, which is titled Software Considerations in Airborne Systems and Equipment Certification. This is the primary document by which certification authorities such as the FAA and EASA approve civil software-based aerospace systems. And the software response to the sensor data is under a few key steps. One is, was it defined correctly in terms of the requirements? Was it implemented correctly, which is verification? And does it do the right thing in operation, which is validation? Levels of criticality in aviation design assurance is shown here from software level A through E, and then the target failure rates. And the catastrophic failure may result in a crash. The failure could cause a loss of critical capability required to fly and land an aircraft. And the target failure rate here is 10 to the minus 9 per hour. And then the steps go down through hazardous to a major failure, to a minor failure, to no effect. The chance of your plane crashing has been published by Harvard as 1 in a million. And the National Weather Service published that the chance of being struck by lightning is 1 in 1.2 million. Hence, the lightning strike risk is 10 times aircraft crash risk. And as we know, lightning strikes rarely occur. And V&V has proven to deliver low risk in the aviation industry. We all fly heavier than air vehicles every day. And as this plot shows, aviation dropped from 3,000 fatalities per trillion revenue passenger kilometers in 1970 to an extremely low number today, roughly 50. The annual risk of being killed in a motor vehicle crash for the average American is about 1 in 5,000. The annual risk of being killed in a plane crash for the average American is about 1 in 11 million. Why the huge difference? I think it is training, discipline, and systems engineering, verification, and validation application in aviation. If we look at drilling, I think it scores high on training, medium on discipline, and extremely low on verification and validation. This is a huge opportunity for incident reduction. Of course, you may talk about the Boeing 737 MAX incidents. And indeed, they went outside the protocol of verification and validation. And the 2 plane crashes were put down to systems failure and to lack of human training. What's interesting to know is that the maneuver characteristics augmentation system installed on the Boeing 737 MAX had been already installed on military tankers from 10 years before. And essentially, the military required multiple sensors, not the single sensor failure point, and greater pilot control in case they didn't like what the plane was doing. The military essentially imposed more stringent verification and validation requirements than the FAA, and this is according to a Wall Street Journal article. So essentially, the system works when it's applied correctly. And how does this get mapped out? Well, systems engineering has a methodology for it, and it's based upon the famous V. And as we can see, we have definition and decomposition on the left, and then we have integration and test on the right. And we start out by validating the concept. What does the concept do what we want it to do? And then at the end, coming back up the V at the same level, we validate the solution. Does it do what it's supposed to do? And then verification is the next level down. So you're verifying the system requirements in the planning side, and then you're verifying that the solution meets those requirements on the test side. And the subsystem verification is the next level down, where there's high-level design, and then there is testing, And then again, you go down to the component verification of detailed design and testing. So essentially, there's a map of moving down one side and up the other side. Essentially, verification is checking that the work product meets the requirements. On the other hand, validation is checking that a work product operates properly in its intended environment. For example, I could verify that a weight sensor on a rig is giving me the right data for string weight, thus deducing weight on bit, but I cannot readily validate that it actually is the true weight on bit. And systems engineering is appropriate for drilling controls and automation. First of all, I look at 4 headings here, and one is significant influence of sensor data and software. So this is similar to aviation. The sensor data and software output influences decision-making by multiple agents, and by agents I mean automation and humans, in manual, semi-automated, and fully automated drilling solutions. Limited assurance is occurring today of the performance of sensors or systems, and consequently, the influence of data and systems on the drilling process is occurring with limited assurance that the sensor output data or the systems themselves will perform adequately, will not fail, nor risk hazardous or catastrophic events. And smart adoption will significantly reduce risk. So adopting the proven aerospace aviation verification and validation methodologies can provide the means to reduce risk in critical systems, especially in automated interconnected systems as occur in drilling systems automation. And finally, we need to evaluate and remove legacy risks. We have legacy sensors which are exposing modern semi-automated and automating drilling operations to major risks that have not yet been evaluated. Right now, there's an industry initiative forming to address verification in automated drilling systems, and this is forming under the Drilling Systems Automation Technology section. Drilling sensor verification to as-built capabilities being addressed through an API recommended practice, which was kicked off by the Operators Group for Data Quality, who'd already done a lot of work in this area, and they brought along IADC to be involved in setting up the API RP and voting on the final product. And then drilling sensor stewardship was addressed through an IADC guide, which is available on the IADC website. For more information, you can contact me via LinkedIn. Thank you for viewing. Please comment below, I will respond, or DM me on LinkedIn. Thank you very much. Bye-bye.